In this class, we will discuss about the Airys stress function in polar coordinates. So you know how to write the Airys stress function in Cartesian coordinates. The Airys stress function will be a function of r and theta in the case of polar coordinates, whereas it is a function of x and y in Cartesian coordinates. So the main thing is, if at all a function phi, which is a function of r and theta, has to be Airys stress function, one important condition should be satisfied. That means we should satisfy this biharmonic equation. Del power 4 phi is equal to 0 or del square phi is equal to 0. So this del square phi is equal to 0 is called as the Laplace equation. So del square is called as the Laplace operator. In polar coordinates, the Laplace operator is denoted like this: dou square by dou r square plus 1 by r into dou by dou r plus 1 by r square into dou square by dou theta square. So here there are three terms here, whereas in the case of Cartesian coordinates, del square is nothing but dou square by dou x square plus dou square by dou y square. That's all. But del power 4, if you want to write, it is del square of del square phi. That means this is del square and another del square phi you have to write. It means same operator connected with phi. So that should be 0. So if you want to say that phi is a stress function, Airys stress function, then equation 1 has to be satisfied. So how to check that? In any given problem, how to check that? So if phi will be given as a function of r and theta, first we have to find out all these derivatives. Dou phi by dou r, then dou square phi by dou r square, then dou phi by dou theta and dou square phi by dou theta square, and the fifth derivative is dou square phi by dou theta dou r. So all those 5 derivatives we have to find out. Then we have to substitute in this. So you are going to get one expression here within the brackets. You are going to get one expression. Then that should be once again differentiated with respect to these three operators, or with respect to these three derivatives, and finally when you add all the derivatives, so that it should be equal to 0. So this is how we have to check whether a given stress function phi is a stress function or not. If at all it satisfies this biharmonic equation, so biharmonic equation, then only stress components will exist. That means there is a possibility of a stress field, we say. So in the case of polar coordinates, there will be three stress components: sigma, sigma theta and cos theta. Similar to Cartesian coordinates, where the stress coordinate components will be, in the case of Cartesian coordinates, sigma x, sigma y and tau xy. Here it is sigma r, sigma theta and tau r theta. So sigma r, in terms of Airys stress function, it is given like this: sigma r is 1 by r into dou phi by dou r plus 1 by r square into dou square phi by dou theta square. Sigma theta is only one term, dou square phi by dou r square, and dou r theta having two terms, 1 by r square into dou phi by dou theta minus 1 by r into dou square phi by dou r dou theta. So by knowing these three stress component expressions, we can always find given a phi, how we can always find stress components. And if they want the stress components at some particular point, so because point means here r and theta, so at some point r is equal to 1, theta is equal to pi by 2, at r is equal to 2, theta is equal to pi by 3, at different points within the element, you can find out the stress field. So by knowing these three stress components. So this is about the Airys stress function in terms of polar coordinates. Now we will take an example problem. So in the problem, what they will do is, normally they will give the stress function phi. So in this problem, phi is given as p by pi into r theta cos theta. It's a function of r and theta. So he has asked find the corresponding stress components. Stress components are sigma r, sigma theta and tau r theta. Of course, at some point he has given. If they don't give any point, you have to write the expression in terms of r and theta finally. Otherwise, if they give any point, so we have to substitute those values. The first value represents r, second value represents theta in radians. So r is equal to 1, theta is equal to pi by 2. We need to find the stress components. So the formula already you know. So these are the expressions for the stress components. So if you check this phi for the Airys biharmonic equation, definitely it satisfies. You can check that. So the del power 4 phi is equal to 0. That condition is satisfied here. You can check that. If you want, you can check that. So 4 up to you have to differentiate twice, and then once again you have to differentiate twice. So finally you will be getting 0. That means phi is an Airys stress function. Only in the examination, if they ask you to prove that given phi is a stress function, then only you have to check this Airys stress for this biharmonic equation. Otherwise, you need not do that. So if they ask you to check or prove, so directly if they ask you to find the stress components, directly you can use this expression. So read out the problem correctly, because it will take time to check this equation. It will take time. If they give, if they have some 10 to 15 marks and if they ask you to check, then you have to do it. Otherwise, if they ask you to find only the stress components, we can go through only these steps. So for finding the stress components, we need to evaluate these derivatives. Please note these derivatives we require. So there are 5 derivatives here. So what are the 5 derivatives? Dou phi by dou r, dou square phi by dou r square. Second derivative. Next dou phi by dou theta, dou square phi by dou theta square. That is 4. 2 plus 2 4. Then dou square phi by dou r dou theta. So 5 derivatives, partial derivatives, you need to compute to find the stress components. So let us do one by one. So when you are differentiating partially phi with respect to r, theta is taken as constant. When you are differentiating with respect to theta, r is taken as constant. So in this given phi, p is a constant. So p by pi is a constant there. R theta cos theta is the variable term. Now dou phi by dou r. So first we will find out dou phi by dou r. Differentiate this with respect to r, treating theta as constant. So p by pi into theta cos theta into 1 you will get. So that is the derivative. Then dou square by dou r square, since it doesn't contain any r term, its derivative with respect to r will be 0. Next, second, dou phi by dou theta. So with respect to theta, we have to differentiate this. Please note that when you are differentiating with respect to theta, r is taken as constant. So p by pi into r, you can take outside. Theta cos theta, you are going to have. This theta cos theta, you have to differentiate using product rule. First function into second function. So you know product rule is like this: d by dx of u into v is equal to u into first function into derivative of second plus second function into derivative of first. So this is called as the product rule in differential calculus. This you have in your PUC product rule. So this we have to use now, because u is theta here, v is cos theta here. So if you differentiate that, you have to recall your PUC mathematics calculus here. So u is theta. So what I will do is, so p by pi into r is constant here. So I will differentiate now. So first function is theta here. So u is theta into dv by dx means theta, of course x is here. We are differentiating with respect to theta, you know. So we have to take with respect to theta, x is theta now. So here you have to differentiate this cos theta with respect to theta. Its derivative is minus sin theta. Then plus second function, that is cos theta becomes the second function v into, for derivative of first function is theta. Derivative of first function theta with respect to theta becomes 1. So that is cos theta into 1. So this is what you get for dou phi by dou theta. Then once again you have to differentiate with respect to theta. You get dou square phi by dou theta square. Now when you do that, so once again pr by pi is constant here. Now you are getting here minus theta sin theta. So if once again you have to use this product rule here. So u becomes theta, v becomes sin theta here. Okay, that minus you can take outside, or you can retain here itself. So minus theta is first function into derivative of sin theta is cos theta, then minus sin theta into 1. Okay, then derivative of cos theta is minus sin theta. So here minus p by pi into r into This I have taken minus outside. All the three are minus terms. I have taken outside. Minus p by pi into r into theta cos theta plus 2 sin theta. This becomes 2 sin theta. So this is the expression for dou square phi by dou theta square. Next, the fifth derivative is I want dou square phi by dou r dou theta. Already you know for dou phi by dou r is this. So if you differentiate this with respect to theta, you are going to get this. So differentiate this with respect to theta means p by pi is constant. Once again, theta cos theta, if you differentiate theta into derivative of cos theta is minus sin theta plus second function cos theta into derivative of first function theta is 1. So this is what we are going to do. Now once you get all these 5 derivatives, partial derivatives, now the stress components can be evaluated using these 3 expressions. So sigma r is equal to 1 by r into dou phi by dou r. So dou phi by dou r is p by pi into theta cos theta. That's what I have written. Then plus 1 by r square into dou square phi by dou theta square, which is this minus pr by pi into theta cos theta plus 2 sin theta. Now if you simplify this, so by taking that p by pi r common outside, if you simplify this, so this theta cos theta term will get cancelled and you will be left with finally minus 2p by pi r into sin theta. So this is what you are going to get for sigma r. This is the first stress component. Second stress component is sigma theta, which is given by dou square phi by dou r square. According to that, it will be 0 here. So we have found out that. So it is not a function of r and theta. So wherever at all the values of r, at all the values of theta, so sigma theta is 0. So there is no normal stress at all in the theta direction. Then dou r theta, this is the expression we have to use, 1 by r square into dou phi by dou theta, which we have found out here, that you have to substitute here. Then minus 1 by r into dou square phi by dou r dou theta. So 1 by r I have written, dou square phi by dou r dou theta is this. This I have written there. Now if you simplify this after multiplication and taking common factor p by pi r, once again all the terms will vanish. You are going to get 0. That means in this particular problem, both sigma theta and dou r theta, they are zeros. Only sigma r exists. Only sigma r means that is the stress in the radial direction. Please note that sigma r is the radial stress. That is the stress in the radial direction. Sigma theta is the stress in the circumference direction. That is circumferential stress. Circumferential stress. And of course, this dou r theta is nothing but the shear stress. So out of these 3 in this problem, for that particular phi function, you are getting sigma theta and dou r theta as zeros. Only sigma r exists for all the values of r and theta. Now, after getting the expressions for these 3, at whatever point he has asked, if he asks to find the stress components at some particular point, just substitute for r and theta the values there. So this point represents that r is equal to 1, theta is equal to pi by 2 in radians, of course. So you just substitute the values of r and theta as 1 and pi by 2 in the obtained expressions for the stress components. Only sigma r exists here. These two are zeros. So at the point 1 comma pi by 2, so that means that r is equal to 1, theta is equal to pi by 2. So what happens to sigma r? Sigma r is minus 2q divided by pi into 1 into sin pi by 2. Sin pi by 2 means sin 90. We had to express in terms of degrees. So sin 90 is 1 there, 1 there. So therefore it becomes minus 2p by pi. So minus 2p by pi is the answer for sigma r. Sigma theta is 0, of course, dou r theta is 0. So these are the stress components at that particular point 1 comma pi by 2. So similarly, they will ask at some other point 2 comma pi by 4 or 3 comma pi by 3. Whatever they ask, just put the values of r and theta in the obtained expressions of stress components and evaluate the values. But be careful, when I already told, when you are using the calculator, if you are typing sine of the angle, so you have to convert that angle to degrees. So pi by 2 should be typed as 90, because if the calculator is in the degree mode, you have to substitute the angle value in degrees, but of course only theta term if it is there, then you can just type pi by 3, that is in radians. So this is how we can compute the stress components for a given Airys stress function in polar coordinates.